morning. Okay, so Victoria is gonna talk about MV topologies and MV uniformities. Please take over, Victoria.
Okay, good morning, everyone. Thank you to the organizing committee, and thank you for giving me the opportunity for participating in this conference. So this is a joint work with Marvi Bolaños, and this talk is a part of a bigger project about MV topologies. So first, I will remember some basic definition and notion about MV algebras and MV topologies. Oh, sorry. An MV algebra is an algebra of type 2 and 0, such that with plus and 0 is a commutative monoid and satisfies these three properties. On each MV algebra, I define the constant one and two more operation, product and subtraction, and has a lattice order. They're defined in this way. The real interval 0, 1 is a standard example of an MV algebra, and it's called standard MV algebra standard. The operations are defined in this form. X plus y is the minimum between the usual addition and 1, and x star is 1 minus x. And a product and minus defined in this way. Meet and join are the usual. Of course, the set of 0, 1 to x of the function from x to 0, 1 is an MV algebra with the natural operations. And note that 0, 1 to x is also a set of fuzzy subset of x. So this algebra, this MV algebra, is that I will consider in this talk. The MV topologies are a type of a fuzzy topology, a kind of a fuzzy topology. This concept arose in a paper by Ciro Russo, in which he showed an extension of stone duality. So a topology, an MV topology, is a subset of fuzzy sets that is a fuzzy topology. Satisfies these three properties, and additional satisfies these two properties. Thus it is closed for addition and product. Addition and product is the MV algebra here. The elements of tau are the open subset, and the element of tau star is a closed. So if we have two topological space X and Y, a map F from X to Y is MV continuous or continuous simply if each open set of the pre-match of each open set of Y is an open set of X, and F is an MV homomorphism. It is bijective, and both F and its inverse are continuous. So we have the category of MV space whose objects are the MV space, and the morphisms are the continuous functions. There are two notions of compactness in this space. An MV space is said to compact if any open covering of X contains an additive covering, it says, for any subset of tau, such that the join of gamma is 1, there exists a finite family of elements of gamma such that their sum is 1. And the space is strongly compact if any open covering of X contains a finite covering. We say that NB space is Hausdorff if for each two different elements of X and Y, there exists two open sets, alpha X and alpha Y, such that alpha X in X is 1 and alpha Y in Y is 1, and there is this join in this sense. So a stone NB space is an NB space which is compact, separate, and zero-dimensional. The category of stone NB space with quasi-continuous maps and morphisms is a full subcategory of NB topological space. So this is the theorem that extends the stone duality. We have two contravariant functors, Klopp and Max, for each NB topological space. The Kloppen is a semi-simple NB algebra, and for each semi-simple NB algebra, there is a NB topology, natural NB topology. These functors are contravariant, and the restriction of Klopp and Max to the subcategories NB-LCC, the limit cut complete NB algebras, and the stone NB space is a duality. And the restriction of such a duality to Boolean algebras and stone space coincide with the classical stone duality. Well, here I finished the preliminaries. Now, this is the diagram that summarizes the duality. Okay, so here we finished the preliminaries, and now I will show some of our results. We prove a Tikhonov theorem. We have a stone-check compactification, and we have a Urison lemma. We define two shifts on NB topological space. I will go fastly over these topics. So this is the Tikhonov theorem in the canonical form. If you have a family of compact NB topological spaces, then the product is compact too. And the proof use strongly this lemma that is analogous of Alexander Soubey's theorem. Of course, is equivalent to axiom of choice. We have a stone-check compactification. That is, we showed that the function inclusion, the Hausdorff compact NB topological space in NB topological space has left adjoint. And we proved that is a good extension in the sense it extends well the stone-check compactification for classical topology, and extend well the stone-check compactification for quasi topologies. Now about normally on an Urison lemma, we inspired by the Hutton's work. Hutton defined a fuzzy topological space as normal if for every closed set alpha and open set beta such that alpha is below beta, there exists gamma and open set gamma such that they satisfy this inequality. And we take this definition and we have a characterization of normality, and MV topological space is normal if and only if for each pair of close fuzzy set alpha and beta, such that they are disjoint. That is, their product is zero. There are two open sets such that gamma is above alpha and delta below beta, and the product is zero. For the Urison lemma, Hutton defined the fuzzy unit interval. For that, he defined this family, zeta I R, be the set of monotonic decreasing function f in 0, 1 to r, such that f and x is 1 for all x less than 0, and f in x is 0 for all x in greater than 1. And he introduced this relation, equivalence relation. F1 is related with F2 if and only if F1 x plus is equal F2 x plus for all x and r. This condition is equivalent to this, where Fx plus is the joint of Ft for all t greater than x. So the fuzzy unit interval is the set of all monotonic decreasing maps F after the identification by this relation. This interval works like a 0-1 real interval for classic topology. So on this fuzzy interval, we define an MV topology, again inspiring Hutton's work, taking as a subbase the family of fuzzy set L, T, R, T with T and R, where L, T, and R, T are fuzzy, is a family or fuzzy set on fuzzy interval, are such that they're defined in this way. So the theorem, the Urison lemma, say that an MV topological space is normal if and only if for every close beta and alpha disjoint, such that there are disjoint, there exists a continuum function from x to fuzzy interval, such that for every x and x, they satisfy this inequality. This inequality is a kind of separation. So I finally we will get into the MV uniformities. Again, our work is inspired by the Hutton's work about uniformities on fuzzy topological spaces. He defined a family of all the functions f from 0, 1 to x to 0, 1 to x with the 3 following properties. And we add this property that is a convenient property that is compatible with the concept of topology. And we define an MV uniformity on a set X is a subset D of B, such that D satisfies again these properties. The 3 first one, like a filter of the algebra, and 1, 2, 4, and 5 are the same condition of the definition of the Hutton's definition. We add this condition for the compatibility with, again, MV topology. So we validate this definition with some results. For example, this proposition, we use this proposition for, we prove this proposition and we use it for generate a topology from the uniformity. So let XT be an MV uniform space. The operator int, the MV interior operator, or the operator int from 01x to 01x defined by int beta is the join of fuzzy set of x, such that for some element of the uniformity, f of the alpha is below beta. We prove this that this is an MV interior operator, and the MV topology generated by an MV uniformity is and the MV topology generated by the MV interior operator. This interior operator. And we define too an MV uniformity on fuzzy interval. Again, we took the Hilton's ideas, and we generate that MV uniformity from these functions and take this function as a subbase. The MV topology generated by the MV uniformity is the usual MV topology, and this is the usual MV uniformity for the usual MV topology on fuzzy interval. We define two a completely regular space, and MV topological space is completely regular for each open set. There are a family of fuzzy set gamma E and a family of maps F E from X to fuzzy set, such that the alpha is the join of this family, and there satisfies again this inequality that is a kind of separation again. And we have this result that again validate the good behavior of the theory. The MV topological space generated by an MV uniform space is completely regular, and the converse is true. If X tau is completely regular in this space, then it's MV uniform. So finally, some our current work and what would like to investigate. Well, this is two words about this talk, and we interested too in convergence theory, uniformities, the topology. We investigate two. We want to investigate 2.3 MV topology or MV frames. What is the concept of MV frames? Study moreover the MV fuzzy interval, because maybe we can do something like algebraic MV topology. This is the some of main reference. Thank you. Gracias. Any question?
Thank you, Luz Victoria. Does anyone have a question?
Muy rápido.
Yeah, I have one. Can you hear me?
Yes, I hear you.
Okay. I was wondering, I mean, of course, if you consider crisp sets instead of fuzzy, you get the usual notion of topology, I guess, right?
My speaking is.
Yeah, I was saying.
My listening is working. So if you.
Yes, if you consider crisp sets instead of fuzzy sets, you get the usual notion of topology and uniformity, right? It's gonna be the same given by Barbieri and Weber, the notion of uniformity on MV algebra.
Yes, I don't know if I got your question, but if your question is the classical uniformity is immersed in this type of MV uniformity.
Yes.
If all classic MV uniformity is MV uniformity, yes.
Okay. And you compared with the results of Barbieri and Weber? Yeah, don't worry.
Sorry, if you can write the question better for me.
Email communication.
Yeah.
Okay, you can translate the question.
No, maybe if I go closer to the computer, I don't know. I guess it's fine. No, you answered, that's fine. Thank you.
Okay, okay.
All right, any other questions or comments? So let's thank the speaker again.